Go ahead.
Okay. If you'll push the button, we'll get started.
We're go.
Ladies and gentlemen, thank you for joining us today. I'm honored to introduce to you Dr. Richard De Veaux as our speaker. Currently, he is a professor of statistics at Williams College in Williamstown, Massachusetts. He is a true Renaissance man with a degree not only in statistics but also in engineering and math and dance education. Dick, you must tell us more about that dance part. He's also author of 3 excellent statistics texts. I have personally used his book titled Intro Stats. I really like that clear, succinct, simple title. It gets right to the point. It is a superb text, overflowing with examples and applications and data and tools for students to use. One feature that I appreciate is a box at the end of each chapter called Connections. Pedagogically, I think this is very effective to expressly and explicitly help students see how the chapters tie together. It also has guidance on using technology and loads of helpful advice for teaching statistics. When I teach introductory statistics, I point out at the beginning that although many people think statistics is math, I tell students that statistics is really philosophy. Dr. De Veaux takes this even further, saying that math is music, but statistics is literature. So, Dick, please explain to us your metaphor. And ladies and gentlemen, feel free to ask questions during the presentation so that we clearly understand the message Dr. De Veaux has for us today.
Well, thank you, Paul. I was going to say, I'm going to leave now and quit while I'm ahead. That was a very nice introduction. But you're absolutely right. This is a talk that I gave at USCOTS last year. So I was going to say, if you've already heard this, you can leave, but Marianne's already told me that she's going to stay anyway, so that didn't work. But I want this to be interactive. I've used these slides actually at some groups about this size where it really is just a way to get us talking about why this course remains so difficult to teach. This is a wonderful time of the semester, I think, to talk about it since I'm just finished writing the final exam for my intro stats class. And like I think all of you, I've done this now more times than I'd like to admit in public. I've taught this course, and it's still challenging. So that's really what I want to talk about today. So please feel free to ask questions or comments anytime. So,
Dick, can you tell us how big your intro stats course is so we know what you're talking about?
Okay, well, this one, the one I just finished, I do lots of different flavors, lots of different sizes. This one is my dream course in some sense. That is, the kids are really prepared mathematically. These are kids who've had probably 3 semesters of calculus. Some of them have had AP stats. So they're not the typical intro stats crowd, but I teach them intro stats. I just add to it statistical computing and about 3 weeks of probability and do everything else that we normally do in intro stats. Mm. And what's hard is exactly what I want to talk about today. It's not the math. Boy, do they get this crowd especially. Boy, do they get it. They just can't wait for me to give them another math problem. But that's not where they fall down. Where they fall down is on the basics of trying to understand what statistics is about and how to communicate it, which I've kept harping to them on it, and it still remains difficult. So, it's 50 kids in a lecture format. Mm-hmm. And we did, at the end of the semester, I listened to 13 projects in groups of 3 or 4, which I made them get. It's an 8:30 class. That's the other wonderful benefit of this. And what the great thing about that is nobody had a conflict beforehand. So the last day I could start at 8 and we could get all the presentations in. You can imagine how thrilled they were, especially this. But we did it. So I titled this Math is Music, Stats is Literature, or Why Are There No 6-Year-Old Novelists? We'll see where this goes. So what it really is, first of all, it's an excuse for me to talk about some of my favorite prodigies. And I think we all agree that we tend to see, here's Gauss on the wonderful 10 Deutschmark bill, which sadly is no longer in existence. One of the sad things about the euro is that this bill is no longer there. There aren't a lot of bills with not only a graphic of a probability density function with the equation right on the bill. I think we should really celebrate that. I don't know which candidate is going to be pushing for putting more probability density functions on U.S. currency, but I think we should all write in for that. But anyway, it's math, music, and chess where we talk about prodigies. And there are lots of great stories about GAISE and about Mozart. My favorite about Mozart is him going to church when he was 5, apparently coming home and playing all the music from the entire service, not only flawlessly, but from memory and all the parts. As I told people, I have 4 kids. I did the experiment. I bought the piano, took them to church, brought them home. I'm still waiting. So, what is it about? So we've got math, we've got music, and then my last prodigy is Bobby Fischer, who sadly passed away a few weeks ago now. But it's always these 3 areas that we talk about. And I think the reason is that these 3 areas, you don't really need any real-world experience. Of course, Mozart's music got more profound as he got older, but some of the stuff he wrote at an incredibly early age, at an age before which he could have possibly acquired the emotional depth and the knowledge about the world that he acquired later, is still profound. And Bobby Fischer's chess at a young age was astounding, as well as Gauss's mathematics. So it's all about rules. And I just went on the web to see about prodigies in literature, since I couldn't think of any. Anybody think of any prodigies in literature off the top of their heads? People have written the great novel by age 12 or 13? Don't all speak at once. So here's the first quote I found on the web. There are no child prodigies in literature, which seemed to sum things up. But then I went to the other source of all knowledge besides the web, which is, of course, Wikipedia, and it listed these 6. And I suppose one can make an argument for all of these. The last one, I didn't know. Henriette Seth F. is actually autistic, and this is one of her paintings. I found her story fascinating. But, it's not a who's who of literature. And I suppose one could... Mary Wollstonecraft Shelley just barely makes the definition of a prodigy as someone who reached sort of mature art form in their adolescence, and she was 19 when she wrote Frankenstein. But I think Frankenstein's a little peculiar, too, because it's really made up. So I think the bottom line here is that literature is about the world and not about rules like math and music and chess, which is, I think, well, let's go first to the blue sheets, which I don't know about you guys. You all know what the blue sheets are, right? It's probably different colors at different institutions. These are the student revenge forms where they get... This is the free-flowing ones, not the little color in the circles. These are the, what could the professor have done better? What was wrong with the course? All those wonderful things. So
I've never heard them referred to as blue sheets. I don't think ours are blue.
Okay. Well, ours are...
But I get it.
Yeah, these wonderful... Ours are wonderful blue, which I guess sort of try to make you feel better. So I just got some comments from them. See if you can relate to any of these. I understand.
Dick, because you're already feeling blue, is that?
Yeah, I think that's it. I understood the material in class, but I found it hard to do the homework. This is my favorite. Should be more like a math course with everything laid out beforehand. More problems in class should be like the homework and the test. Or maybe vice versa. And how about this one? Say what we need to know and don't add anything else. I try to tell them that the everything else was the course, but they don't quite have that perspective. And what's the reason for this? Part of it, I think, is, well, I fought for a long time at Williams. I finally won the battle, but to have my courses listed, as Paul said, it isn't math, but all my courses were listed as math. And so that's a first marketing problem. If it says Math 143, and the kids come in, and you're not going to be axiomatic, they get upset, and rightfully so. So finally it says Stat 101 or Stat 201, but I don't think they really know what that means. That's part of the problem that we have. So
well, that actually helps because it takes away the math aura.
It takes away the math aura and the math expectation. So at least
right.
we know there they're up for something different. They just don't know what it is. But we're still a math stat department, and I think they still expect it to be more axiomatic.
Mm-hmm.
I don't know, some of you teach calculus still, Catherine?
I haven't taught it recently, but I did teach it.
I told, I've got some pretty famous teachers of calculus in my department, and I was telling Colin Adams that I had a dream the other night that I got to teach calculus. And he gave this really funny look. Was that a good dream? I said, it was wonderful. And he said, why? I said, because of exactly this. I said, I could come up with one problem, which was this sheet of cardboard 3 feet by 4 feet made into a box, and you cut equal size squares. What's the dimension of the box with the largest volume? And then once they got that, I had an infinite number of new problems that I could generate just by changing the numbers. Isn't that great? I said, imagine doing that in statistics. People have average heights of 5'6". No, we're going to change that to 7'4", and then 3'2", and then just change the numbers. It doesn't work. We have this horrible thing called context. So I pulled out a typical stat problem, and we don't have to go through all the details, but what's clear is in here is there's lots of stuff about the world. It's actually about subjects who consume dairy products, and it was more than this number of times a week, and they got this insulin-resistant syndrome, and these people didn't eat as much, and, what's the evidence that the risk is different, et cetera. And some of my students say is, you really expect us to know a lot. I expect them to be able to sort through the real world and give some judgment, which is asking a lot out of an 18 or 19-year-old. So what's the hard part for statistics? It's putting all this stuff together. And I just had a student come in and ask, our finals tomorrow. So he said, oh, professor, he said, I think I understand everything in the book. He said, and if you just put what chapter it was from on the final, I'm sure I'd do really well.
I had the same exact request about 2 weeks ago. Same one.
Right. It's just, it's just how I feel about the French. If they would just have subtitles on their chest or something so I could just see the words as they're speaking it, I would understand everything too. But life is cruel, and we're not going to give them the chapter and tell them what it is. I'm sure most of you know Roxy Peck. She has this wonderful phrase about all of us being the troublemakers in statistics, because we've changed this course from when some of us started teaching this years and years ago when it was easy to teach. And it was easy to teach because we just taught formulas.
Mm-hmm. Right.
That was great.
Well, Dick, I've wondered whether maybe reading comprehension might be part of students' problems. They're not used to reading so critically.
I think that could be part of the problem. I don't think it's. I would be surprised if it's the problem where you are so much and where I am.
I have foreign students who don't have English as their first language.
I do too, and that's certainly. And then I just brought this up at a faculty meeting because we were talking about writing across the curriculum and what we're doing for these foreign students to help them, because English isn't their first language. They have trouble reading, and boy, do they have trouble communicating. And now I'm stuck with, when I'm grading communication, how much weight do I put on correct grammar and expression and all the things when a student clearly is struggling to communicate, to express themselves? I don't have the answer for that, but clearly that's why it became harder for us, certainly harder to grade.
Well, I think people teaching in middle school and high school are going to have the same problem, but they're dealing with native English speakers who don't have the experience, perhaps are not strong readers,
right,
and certainly not strong writers.
Right. It's certainly a challenge. I mean, we're making them both read and write, and we were talking. They were my faculty meeting. They were talking about these writing-intensive courses. They were thinking of dropping the number of students in these courses from 19 to 14, so they could really concentrate on drafts and their writing. And I just thought, I just graded 50 writing-intensive second midterms, and boy, it just took me forever. But I don't know what else I'm going to do. I'm not going to go back to saying, fine, you computed the standard deviation, it was 3.12, congratulations.
No, we can't go back there.
I'm not going to do it. So I don't have an answer here. I'm just sympathizing with everybody and saying, yeah, we've made it hard, and here we are.
Mm-hmm.
So this is my favorite cartoon about this, Hell's Library, where he looks down and he sees what the reading list is going to be in Hell's Library. And all story problems. And I think that's what students find about stats, right? It's just
yes, it's cute.
Excuse me. Okay. So back to my teaching calculus, and I don't want to say anybody who teaches calculus, I don't want to say it's easy. But on the other hand, here's, I think, a pretty complete list of the major concepts in the first semester of calculus. I've listed 3 of them as should be review, and then the big ones are the derivative and finding maxes and mins and maybe implicit differentiation and then reversing it. And then the big news at the end is linking the 2 together, and it's time for the final.
Mm-hmm.
And I thought, well, what are we trying to do in introstat? Here's a list. We're just asking them to be experts in exploratory data analysis. It's probably a lifetime goal. Talking about data collection, the easy topics of randomness and variation, which of course everybody finds completely intuitive. The trouble is you can't see my tongue firmly wedged in my cheek over a webinar, but this is probably the hardest concept in the whole course. Then we get on to inference, confidence, significance, the scientific method. We're talking about models, and as soon as we give students models, we talk about limits to models. I call that the build the rug and then yank it out from under them. They're standing on it, approach the statistics, which we all do. And then we wonder about, should we put a few weeks of probability in this? Because they really ought to know that too, because we have so much time here in 12 to 15 weeks. I think it's amazing. I mean, I keep saying this across the country. I think it's amazing that we put up with the fact that calculus gets 3 semesters, 2 semesters, 3 semesters, and we're supposed to do all of this in 12 to 15 weeks.
And you don't even have sampling distributions on your list there.
Oh, it's coming. I hit it. Yeah, that's the elephant lying under the rug.
Right.
It's coming. And, of course, then we want them to interpret all of this and communicate it to people who don't understand this.
Mm-hmm.
And that should be easy to do in 12 to 15 weeks. So I'm going to just go to my love, which is data mining, and just show why I think this is challenging. So I thought I'd be really brave and try to do this live. Should we try to do that, or we try to do a little data analysis live here?
That would be great.
Let's see if I can do that. So it's going to ask me, I think I have to go to share. Oops. What happened there? Oh, it pops up. Okay. Okay, everybody see that?
Yep, it's a data set.
It's a data set. And not only is it a data set, but I'm just going to do this. These are the variables.
Dick, wait a minute. Does everyone see it?
Yes, I'm seeing it.
Okay, so let me go back and explain a little bit about what this data set is. It's a real data set from a philanthropic group called the Paralyzed Veterans of America. This was used in a competition about 10 years ago, in fact, almost exactly 10 years ago now, a data mining competition where the objective is for this group. Anybody get mailings from the Paralyzed Veterans?
Oh, all the time.
Yeah. If you're on their list, it's exactly as all the time. In fact, it's every 6 weeks. That's their strategy. Their strategy is to send you a gift, typically address labels or greeting cards, and ask you if you'd like to contribute again to the Paralyzed Veterans. They are the government-sanctioned representative of the Paralyzed Veterans. Unfortunately, I taught a course like this to a lifelong learning group last year. They all knew the Paralyzed Veterans. Some of them said, I don't give to them anymore because their efficiency is so low. Efficiency being how much they have to spend to get $1 to the veterans. And the reason it's so low is their strategy is so bad. This sending every 6 weeks to everybody on their list is expensive. It costs them about 67 cents per person to send out gift plus mailing.
Mm.
And their average return is about 78 cents. So, that's net. I mean, they're getting net 11 cents a person, which is about $11,000 per 100,000. So the object of the contest was to see if we could come up with a better model. So here are the data. Now, just Just watch, just have a look at this. I mean, this isn't what I would do in an intro stats course, but this is the data. So it's 479 variables on everybody in their mailing list.
Oh.
So, Catherine, you're in there somewhere. And we have 479 pieces of information on you.
Oh.
So just imagine starting this process. You know, I don't think I was taught this in graduate school, but somewhere along the way I learned that the first thing you should do is plot the data. Well,
how many observations do you have?
Oh, I should say that. I have 94,649 in the training set. And that includes this last variable, the variables at the end here. Let me just go to that. There's two variables, two responses. Target B, which says, did I give or not to the last campaign? And those are zeros, ones. Here's a 1. That's somebody who gave. And target D says they gave $4. So here's the next person. They gave $7, etc. So it's 94,000 of those. I won't do that again. And then you get another 100,000 with all the information except target B and target D, and you're supposed to come up with a model that says, who should I mail to maximize my profit? So that's the contest. So that's not really what the relevance for interest stats. I just want to take one variable back here, and I want to look at its distribution with everybody. So this is a variable called T-code, and we're just going to have a look at it. So here it comes. I'll turn this is jump. I don't know if you know it. It has this peculiar thing. It has a few peculiarities. I like jump, but it's peculiar in that histograms come up sideways at first. So here's the histogram of T-code. I would say this probably is not the first histogram you want to show in intro stats class. Explain what a histogram is. It's a little strange. And this is the box plot. You see the box there?
Not exactly.
That's the box. It's so squished. These are all outliers. And the only thing, the vertical axis actually doesn't mean anything, but because they're repeat points, it puts outliers on the same, it stacks them up.
Okay.
Kind of a weird thing. But basically what we see here is an incredibly skewed distribution. Let's look at some summary statistics just to review the simple concepts of mean, median, and mode. So we have a median of 1 and a mean of 54.413. Again, maybe not the first example we should give an intro stats class, or the interquartile range of 2 with a corresponding standard deviation of 957. So, what's going on here?
What does T-code tell us? What is it?
That's a great question. And, you know, it'll be about, I love to watch how long it takes students to ask that question.
Oh.
Because some of the kids, I get this, especially in this group. This is a mathy group. So some of them will say, Professor, maybe we should try a transformation. You know, so I say, what transformation would you suggest? They say, well, you know, I'm in chem lab and we always use logs. How about log? I said, well, we got a lot of zeros, so let's add a little something to that. So let me unshare this for a second. How do I go back, Rick? Where did I go?
Oh, there's a little arrow on the toolbar on your screen.
There's a little arrow on the screen. I have to get back to somehow to the application. Stop sharing?
If you do that, then you'd have to begin sharing again, but that'll work too.
Okay, well, I don't think I'm going to go back there. Let's see. Where is, I seem to have lost my slides.
There's a little blue arrow in the bottom right-hand corner of my picture.
Right.
Oh, yes.
Getting close.
That little arrow says return to main window. Thank you. The one. Okay, we'll put that over there. All right, so there's the dead picture of it. So there's the histogram. Let's go through the slides here. We've seen that. There's a blow-up of the box plot in case you wanted to. Yeah, there are those outliers. So here's the log plus 0.01. Didn't help us a whole lot. So, you know, what I love is that a lot of times we teach these rigid definitions of quantitative or categorical when, for me, it seems like all the variables I deal with are somehow neither one or both, or sometimes one and sometimes the other. So I just thought, well, let's look at it as categorical. So what do we see? We see this big spike at 0, 1, 2, 3, 4, and a spike at 28, a spike at 1,002, and the max is 72,002. So I'm going to get to Catherine's question in a minute. In fact, I'm going to get to it now. Here's what T-code means. It's the code.
Oh, you're kidding.
It's the code they use to put in front of your name on the address label.
Oh, dear.
Oh.
So 0 meant nothing.
Nothing.
1 is Mr. Dick De Veaux, or Mrs. Dick De Veaux, or 2002, Mesdames Dick De Veaux. Not so used, but we have Rabbi Dick De Veaux at 9, and 28 was the spike. That's Ms. 1002 was another spike, Mr. and Mrs., oddly enough. And these over here on the right are real. I didn't make these up.
Your Highness?
Your Highness, His Highness, Your Majesty, Prince and Princess, Your Imperial Majesty, all of those are real. And I guess if those are true and you don't use those, you probably aren't going to get the donation. So the point is, of all of this is, what's hard about this? It's not computing the mean. It's not even understanding, as some of my math students will say when I say, what does the mean of 54.41 mean? And they'll say, well, Professor, what you've done is you've summed up all the observations, y sub 1 through y sub n, and you've divided by n the sample size, et cetera, et cetera, et cetera. It doesn't mean anything. So it's the big question that Catherine asked. What does it mean? So here's
a great example.
So here's an example, another example of pulling the rug out from under them. So I love this example. I think I got this from Larson and Marx, which I love that book for teaching math stat when I used to teach math stat. But that's another story. So this is the University of Texas football team's weight from 1905 to 1965, the average team weight. And this is an actual picture of them in 1893. When you can see football was a different sport when they weighed about 160 pounds on average. So it was really more like rugby. And people were smaller then too, I guess. But there they are. So, but that's pretty linear looking, isn't it? I mean, it's not terrible.
Mm-hmm.
So I fit a line. I was brave, and I've clicked the right arrow, and it seems to not want to do anything.
It looks like something changed between 1920 and 1940.
Dramatically. Yeah, that looks like a strange outline. I don't know what was going on then. Rick, I've got the hourglass on my web meeting.
An hourglass?
I've got an hourglass. I clicked to the right to go to the next slide, and it gave me the hourglass.
I think that should resolve itself pretty soon.
Hoping.
So we have a side webinar on Isn't Technology Wonderful?
Let me change, Dick, let me change the presenters back to myself.
Okay.
And then
there it is.
It's back.
I'll go back to you. How does that work for you?
I've still got an hourglass. So I'm wondering if it's a problem on my end with something. Hang on.
Why didn't you call me back?
This computer has been having some, as we say, issues recently with connection, and it's just sometimes somebody takes control of it and it doesn't come back for a while. I suspect that happened here. In worst case, what I'm going to have to do is just power this machine back up and come back to you guys. It shouldn't take too long, but I don't want to hang everybody up waiting for this. Something. I just hit Control-Alt-Delete, and it's not really doing anything.
Do you have another machine to work on?
I do. Usually this works. Yeah. Why don't I do that? Why don't I switch machines and get right back to you guys?
Okay, that sounds good, Dick. We'll hold tight.
And I'll just hang on.
We can just discuss your slide.
Let's see now. What can I do?
Can anybody hear me there?
Yep, we can hear.
All right. I'll probably have to leave because of something else I have to do. But I was wondering if you guys who teach statistics like me would be willing to exchange emails on this topic about how to be more effective in teaching with examples and illustrations.
Absolutely.
I would like to exchange emails with other people who teach statistics.
Okay, we'll
I don't
take care
have
of that.
anybody.
Rebecca, you have the list, so we can put together an exchange list and do exactly that.
Of course.
Yeah, because I was here quiet looking at his, especially the beginning part of the discussion, and the types of questions that students raise seems to be the same across. It's been like this with me for 6-7 years, and he mentioned the same type of questions, and maybe the most typical one I hear is that they understand everything in class and they go home and cannot solve it.
Absolutely. Absolutely.
So I thought if maybe it would be beneficial for us to.
Well, part of the issue is on our sidebar here, while Dick's getting the technology working again. As a sidebar, part of the issue is the difference between what students think learning is and what learning really is. And Dick's point is entirely valid. They think memorizing rules is learning something.
Right.
And oftentimes that is simply not the case. And you can't just do a statistics problem in some kind of a mechanical, algorithmic way. And especially textbooks I have an issue with that teach statistics exactly that way. Do step 1, do step 2, do step 3, and by the time you get to step 4, you've got the problem solved. Statistics simply doesn't work that way, and that's what Dick is illustrating right now. So a forum within which we can exchange ideas back and forth in helping to identify not how to teach statistics, but how to help students recognize what learning really is in learning statistics will be beneficial to us, but it'll be beneficial to them too, because in my view, when you learn how to learn statistics, you learn how to learn.
Right. Right. Well, I have to go, but if I may be Rebecca, who has all the emails, if you guys are interested, maybe we could start a small list, a discussion list.
We'll put that together.
Is very practical. I answer like tons of emails a day, but if you tell me go to the discussion forum, I never go. I don't know.
Yeah, I'd be better with listservs too.
We'll get back with you on that directly. Rebecca, when we get finished, you and I can chat further on that.
All right. I have to hang up because I have to go somewhere.
Thanks for joining us.
Sure, thanks.
Thank you very much.
That's the point of this.
And by the way, I do have Dick's book. And I want to just put a footnote here. I'm a chess player and the director of a chess club. Thank you for putting Bobby Fischer down.
My pleasure.
I'm going to a chess club meeting now, so that's why I have to leave.
Well, have fun. Dick, are we back up again?
I think we are. Look at that.
I look forward to getting an email from Rebecca. Thank you.
Okay. I'm seeing something. Are you guys seeing it?
Yep, we see your regression line.
Okay, so there's the regression line. So, and, one could argue about, of course we teach the dangers of extrapolation, right? I mean,
Sure.
that's the first thing. But let's be brave here. Let's predict 2005. So I did that. And it says the predicted weight is 228.21 pounds. Now, I went to the web and looked what the actual weight of the 2005 team was. I really had no idea what that was going to turn out to be, but it's pretty extraordinary. So maybe not a great example for dangers of extrapolation. Kids are going to think this is just the best tool since sliced bread. There it is. It's within 1/10 of a pound.
My God.
Yeah, and so it's gone up 2/3 of a pound on average for more than a century, and just spot on. So now I got really excited. So now I went to the Div 3 powerhouse team of Williams College, and I have access to some of the programs from the 70s and 80s and early 90s. So I thought, well, let's just do the same thing here. And so I spit a line. There are the mighty Ephs on Spring Street recently. And so my data stopped in the 90s, but I went ahead and predicted them. Whoop, we lost one here. Oh, I guess the equation's gone. But the equation says that they should weigh currently about 216 pounds on average. And I asked a couple of my kids in intro stats who are on the football team, I said, is that unreasonable? And they said, no, it's about right. It might be a little bit exaggeration, but that's just about it. So I thought, okay, well, here's the bottom line. I'm often asked by the president to do certain statistical things, and I thought, well, if we're going to plan for the tricentennial of Williams College, we might as well predict into the future to 2093. And armed with this, it looks like about 2040, we're going to be passing Texas. And by 2093, it shouldn't be much of a contest. So I told him to go ahead and put Texas on the schedule for the tricentennial game. So there we go. So, so my point, what do we expect students to do with this? So they're told it's not a good idea to extrapolate, but it works sometimes, and that, of course, if you go too far, it's ridiculous, but they're supposed to have the judgment and maturity of somebody who's been doing data analysis for 20, 30, 40 years after this comes in, about week 6? It's just extraordinary, and we wonder why they find it difficult. So I'm going to quickly go through this. This is due to my colleague and co-author Paul Velleman, who said what's hard is that we're making them do 5 unnatural acts of thinking. And the first one is we're asking these kids to think critically, which we don't ask them to do it certainly in any math course that I know of. Maybe in an advanced modeling course, but in calculus, I never heard the question when we talk about finding, the water in a cone and it's dripping out at this rate. The kids don't raise their hand and say, how do we know that's really a cone? It's because we said it was a cone, and that's the end of the story. So the first time we give them data on week 1 or week 2, we say, well, you should really ask how the data were collected and what the credentials are, and we should worry about that. And they're still deciding what course to take. And then we ask them to be skeptical, which should be easy for 18 and 19-year-olds. It should be something natural. But again, this is really the pull the rug out from under them as soon as we teach them. As soon as we teach them a method, be cautious. So learn all these methods and trust every analysis, but be sure to plot the residuals because the unexpected can always happen. And not only that, but we explicitly go looking for it.
Dick, can I interject?
Absolutely.
It seems to me sometimes they confuse being cynical with being skeptical.
Yes. We want to be skeptical, and here's a great example that I got last night in my review session. So a student said to me, okay, Professor, we know we're supposed to check the assumptions and conditions, but on the final, if the assumptions and conditions aren't met, can we just say, I'm stopping? What a great question. I said, well, in real life, we have to make a judgment about how those assumptions and conditions are violated in order to know how cautious we should be and when to say no. And that's really a difficult question. It's a profound question.
Mm-hmm. It is.
And one of them was the success-failure condition for testing a binomial. We say, you should have at least 10 successes and failures, or else the normal model isn't going to be very good. You shouldn't do a z-test, certainly. And, of course, there's not time to tell them how to do an exact test, which would be great if we had another semester. So we say, be careful. So I said, imagine this. We're testing whether a roulette wheel is fair. So let's forget about the green slots for a minute. Just the red and blacks, 50-50. We're trying to decide whether P is 0.5 for red. And we spin it 100 times. And we get 2 successes. We get 2 reds. I said, I'd be really disappointed if anybody said, okay, I can't really say anything about whether this is fair because I only got 2 successes, and that's not enough. And they got it, but I had to technically say, well, in that situation, since you have a null hypothesis, that's the success-failure condition you ought to be looking at. That's the normal model we're using. But it made me realize how subtle that is for intro stats course, and yet that's our bread and butter.
Mm-hmm.
It's just a lot of stuff. And then, of course...
But, Dick, isn't the danger then in teaching skepticism, scientific skepticism, that they slip into the easy mode of just being dismissively cynical? Yeah,
I think it's a real tricky balance. And I think it's true in industry.
Exactly.
I go out in industry all the time, and statisticians have this terrible reputation of just being naysayers.
Right.
Just telling everybody their data aren't good enough and their assumptions aren't met, and no, this isn't statistically significant, et cetera, to the point where nobody wants to go down the hall to see the statistician. It's a problem we have.
My engineering students are saying, well, statistics is a bunch of hand-wavy stuff.
And then there's that. So we're right. We're too negative, and yet it's all mushy. You can say anything you want with statistics.
Right.
We have a lot of marketing battles. It's part of our challenge.
Mm-hmm.
And then, as this slide points out, not only that, but unlike every science and math course, instead of concentrating on what the theory that's being presented says, we focus on what it doesn't say. What I mean is, we don't say things like the mean's 31.2. We don't say it's probably 31.2. We don't say it's close to 31.2. We say it's close to 31.2 probably. And then we go on and on about exactly what that means and how wrong it is and how often it's not going to be true and whether the confidence interval is varying or the mean is varying or what exactly, who's standing still and who's dancing around it. And at that point, the students are justifiably challenged.
That's why they say it's a bunch of hand-waving.
Right. So like I said, I have no answers here today. In case anybody was hoping for answers, I'm just pointing out all the challenges that we all know, but I just thought I'd write them down.
It does make me feel better that you're having the same challenges that I'm having.
Well, I'm glad you find solace in that.
But I was hoping for an answer or two.
I'm hoping to get to that. Let's see.
Okay.
I joke that this is an easy concept because this is the hardest thing, is that no one, especially engineers, Catherine, right? They hate thinking about variation.
Oh, absolutely.
You want to think about the mean and just, God, can't we just get that precision? Well, somebody told me a funny story about going to the Mercedes plant in Germany and being so impressed at how well the trunk fit. And he looked at the quality control engineer in charge and said, what's the tolerance on that? And the guy looked at him as if he'd insulted the man's mother. Said, there is no tolerance.
Right.
That was a real engineer, right? I mean, it fits, damn it. We're not talking about any kind of plus or minus anything. I love that. If you want tolerance, go buy a Japanese car. So then we get to the last topic, which is probability, and I love teaching probability. It's a great, fascinating subject. But first of all, I don't know how to fit it in to my normal intro stats class. I fit it into this class only because I just this is a fire hydrant course, which I don't recommend for anybody. I mean, these kids, we really need to separate out Stat 101 and 201 for these kids. And I said, this is really a course for kids who've had 3 semesters of calculus and stats already. It's still called intro stats, but it's a review and other stuff. But in my other course, where I have anthro majors and English majors, I don't know what to do with probability.
I try to do as little as possible.
Yeah, I want them to know that the p-value is a probability and what that means and what conditioning means.
Right,
but
right.
The rules, all that manipulation, there's just not time for.
So you really do cut that out? I'm still trying to fit it in.
I really have cut it out. I know it's easier to talk about the sampling distribution if you've gone through the binomial, but I have so few warm bodies left after I've gone through the binomial that I'm not sure it's worth it.
Okay.
I go back and forth. I think it's worth doing the experiment. I mean, that's what David Moore decided when he went to basic practice. Long ago, I remember asking him at a conference, I said, so what's the difference between the red book and the orange book at the time? And he said, well, I got rid of probability. And I looked at him with the same expression you're thinking, really? How can we do that? Try it.
The students who are the social science majors have just huge trouble with the course.
Yeah.
And I think if you just get them to have the idea that you can't expect things to be the same every time you measure it, that things are going to vary, that you've made big progress.
Absolutely.
Catherine, you said it exactly right. The issue isn't probability. The issue is variance.
Right.
Yes, so variability.
If you can talk about, variance, variability, variation, whatever the synonyms are that work for them, that's the concept that they need to walk away with. And then probability is simply a way of quantifying that.
Exactly.
Right. I agree with you, Paul.
Emphasize the former and de-emphasize the latter.
That's it.
And the other concept I'm thrilled if I get across at all is that all of this is really a tool to help them make better decisions, not a tool for making decisions. It doesn't make the decision. This idea that .051 is different than .049, that the social scientists seem to have, they celebrate. I just think we have to fight all the time. I want to put the responsibility back on them. They're going to have to go out and make decisions under uncertainty, and these are tools to help them do a better job. And they're going to make mistakes, and they should know some tools for quantifying how often they do that. And that, if I can get that and variability across in a semester, I'm thrilled.
Absolutely thrilled.
Yeah.
You know, if we can teach more of these concepts all the way K through 12, so the kids get the idea of things varying, they wouldn't be so surprised.
And thank you, Catherine, because that's our point for today. It's not intro stats at college level. It's how do we get people thinking this way when they're in high school, when they're in middle school, when they're in elementary school.
Yeah. The more
they
experience
can understand it when they get into high school. I mean, into college. Excuse me.
Right.
And what I see is a double-edged sword because I have my youngest is now 13. I've watched this introduction of statistics into their curriculum with joy as they bring this home. But then I also see it's taught as math. Here's how to compute the mode. Here's how to compute the median. Here's how to compute the mean. Did you get that? No teaching often of why you would do this and what these things mean.
And they do the same frequency distribution of which sport is your favorite sport every year.
Yeah.
Without any thought of what would I do with this if I actually had this data.
Right. Because to be fair, the teachers don't know. We're
they
not.
They don't.
We're not educating them.
No idea.
We need to do that. Yeah, my son came back from kindergarten and said, "What's the candy with the orange and black square wrapper?" And I said, it was right after Halloween, and I said, I think I know, but why do you ask? And he had this beautiful bar chart of all the wrappers on there. I thought it was really creative, but again, they didn't know what they were doing. They said, well, everybody gets these, you know. And all these Reese's cups with the tallest bar. And I said, okay. That was great. So I don't know if you've seen this. This is what I love. This is my favorite example. This is Tversky and Kahneman's example about why probability is difficult. The example is Linda, the 31-year-old outspoken, bright philosophy major who's interested in social justice. And then we ask people, so they get this picture of her, and then they say, rank these in order of likelihood. What's more likely? And the whole thing is a wonderful experiment where most of this is just disguising. What they really want to see is which do people rank more likely, F or H? Linda a bank teller, or is Linda a bank teller who's active in the feminist movement?
Well, they probably say H, and they should say F.
Exactly. They say H because they have this idea. Well, obviously, and they rank that as more likely because they know her. Just as if we say something with floods and what the damage it could cause, and we put subsets inside, people have no idea of how to do this. So now they rank it higher than either of you. I forgot C. So they rank the intersection is higher than either of the two larger events. Of course, we teach something like this, but it doesn't seem to stick.
I'm so amazed.
Yeah. We wonder why. It seems so clear, doesn't it?
Right.
Right. Okay. And then this is just my, many of you have seen this. Is my favorite example of why we're so bad at randomness and variation. Pick a number. I do this over and over and over. This is a typical distribution, which is really fun to do in a large class because you can write this on the board underneath the slide beforehand. You can just hide this, and then you have people raise their hands, and they think you've got ESP because they always do this. They always say 3. About 70% of them say 3. We're bad at random. This is an experiment done recently. They're asking to pick a number between 1 and 10. Psychologists can tell me why they're modes. There is the strange student who said 12. No. So now let's talk a little bit about possible ways we can help, so we don't just end this on a very depressed note. So we've talked about the guy who left said it exactly. Talk about making sure that all the examples really speak to them. And I don't know about you guys. This is where I spend all the time preparing the course, trying to find new examples. If we talk about the 2004 election, and that's so yesterday's news. They don't remember who ran, who won.
Right.
So I have to tell you this great story, though. I was talking about the 1936 election, and Catherine, you're talking about international students. I had a wonderful kid from Pakistan at Ashek Shams, and he's very diligent. He reads the chapters beforehand. He's just a wonderful spirit to have in class. And he came in, and I said, we're going to talk about the 1936 election. That's a Literary Digest, famous election.
Right.
Does anybody know who ran? And he raises his hand, and he says, oh, I know. He says, I know. He said, it was Landon and somebody, but I can't remember the other guy's name. And even my sleepy American students realized that was funny. First time I'd ever gotten that response. Landon and what's his name?
That's great.
So you live long enough, you'll see almost anything. But one thing I try to do with my consulting, I was just at American Express yesterday. I was saying the same thing to people who are using this. I said, what's the most important thing to do in solving a statistics problem is to figure out what the problem is first. Figure out what we're trying to do and why we're trying to do it, instead of just diving into the data. Everybody's so apprehensive that they just want to get into the mechanics of the problem before they even know what they're doing. So plan first. We get this right from Deming, right? Plan,
sure.
Report. It's as simple as that. It's 1, 2, 3.
What I find people ignore entirely is what's the question.
Right.
They don't even think about it.
No, they want to know what
problem and haven't answered it.
Right.
They've done lots of mechanics and there's no question answered.
And I think it's their phobia about what this is about. Is they're so uptight about getting the math right because that's scary that they forget that it's not it at all.
Right.
And less all the time. I mean, I said my kids, they just want to calculate because they're good at it. And I say, you know what, you guys are good at it, but my software is better and a lot faster. So, I'm not going to give you a standard deviation to calculate, even though you'd love that. You'd love to show me how you can do that, but I'm not going to give you the pleasure. Get it. I'm going to give it to you, and you have to explain it. And they all give me these groans. So I just put GAISE up here because other people smarter than I have said these same things. And there's a partial list of the people who said it, that we should do all of this stuff. I love, I'd love to be able to do all of this in my course all the time, and I have to pick and choose with 2 lectures a week of 50, but but they're great guidelines. And I don't have the answer about order of topics either. I'm constantly experimenting. How much probability, what to do. I think there are a couple things I've found that, as much as we want to say everything on the first day, that it's confusing to say everything that we're going to talk about, unless we do it in a very broad brush way. But trying to get the idea of what a population, what a sample is, what's random, what's inference, what's bias, all that stuff in the same day is hard. But I don't know. How many of you are on the isolated isostats listserv? I know Catherine.
I am. Yeah.
I am too.
There's been a great discussion about shouldn't we be teaching more modern methods recently, right?
Yes, that was interesting.
Yeah, and for this class, my advanced class, that's exactly what I've been doing. I put a randomization test on the first day. I just appeal to their intuition. And I don't see any, there's a lot of discussion about shouldn't we just scrap everything and do this. And I think first of all, talk about the troublemakers. This is the radical fringe. And we could go do this. And everybody said, let's write a textbook for this. Well, it would have an audience of the 30 of us.
Right.
Now. But I think we have to drag the rest of the stat world slowly, kicking and screaming along. I think it's a great idea. But I think what it's great for is reinforcing that, for example, that the t-test is really trying to approximate that distribution. And that we can look at it, but when some reasonable assumptions are satisfied, here's a really automatic way of doing it as well that summarizes it. And of course it has limitations, but look how close these are. And I found that to be a great link for this. I don't know how to get it into, the 12 weeks of beginning intro stats yet.
Right. I agree with you.
Yeah, but it's a lot of fun. But even
I don't think I'd go that way with the social sciences students or with really young kids either.
Yeah, I know, because it's very sophisticated in a way. It's very intuitive and I need more experience with it before I'm going to do that. I say that I'm probably going to do it in the fall. I have Stat 101 with 90 students, and I'm probably going to show them some stuff and see what a disaster it is, but I'll let you know.
Well, I'd always try to do a few randomization tests.
Right.
But and some bootstrap confidence intervals.
Right.
But I think
with social science students even?
No, with my math students.
Okay.
Right.
You're just dealing with a different group than I am.
I think with the social science students, sticking with really thinking through what is the problem.
Right.
And the traditional methods.
Right.
And getting them to think much more about the problem. I think that's the way you have to teach kids, too. They have to think about what's the question, what are we trying to gather the data for, or what was this data gathered for, where did they get the data?
Exactly. I couldn't agree more.
That's, I think, where you have to deal with younger kids and with the social science students.
Less sophisticated, mathematically. Yeah.
Well, let me interject. I think that's where you have to do with the math competent students as well. You've got to stick to, in the intro course or the first time through course, whatever it might be, however it might be characterized, you have to stick with basic principles, basic thinking principles, basic concepts of thought and approach to problem solving,
right.
Not to the mechanics, as you're saying, Dick, of doing mathematics.
Right, but at the same time with those kids, for example, one of them said, this distribution looks a little skewed. I'm worried about applying a T confidence interval to it. And I said, well, that's great. I said, why don't you take a bootstrap samples of size 30 about 10,000 times and look at the mean and see what the sampling distribution actually looks like? And they looked at me and they said, oh, yeah, we know how to do that, don't we? And they did it, and it was fine, and they felt really empowered.
Did they compare it to the T confidence intervals?
No, I didn't use it for a bootstrap confidence interval. I just said to see whether the sampling distribution was symmetric.
Oh.
Just to get a sense of whether that asymmetry was strong enough to mess up a sample of size 30. They did, and they said, no, it looks perfectly symmetric. I even did a normal probability plot, and it's pretty straight. I said, well, there you go. Looked at me like, oh, my goodness, we can do this. So, I think maybe just introducing that instead of these rules about 30's okay and 40's better, and by the time you get to 50, you're fine. I can find real distributions where 50's not fine.
No, sure.
Yeah, and I can find real distributions where 7's perfectly wonderful. So,
yep.
So just that alone, I would do that. I might even do that first, is just have them simulate the sampling distribution of means by bootstrapping.
I hope that's one of your messages for today, because I certainly see our world that way. Teaching the rules is entirely dysfunctional to the process of learning statistics.
Absolutely. And that's what the last of this slide says is, tell them that these things are imprecise right up front. These are not math concepts. Is it skewed? No, I'm not going to give you a measure, and if it's bigger than 3, then it's skewed, and if it's smaller, then it's not. And kids find this hard. Is it unimodal? Isn't that great on, first week, and they're arguing about whether it's unimodal, and maybe we should look at how many counts there are on the y-axis before we get too excited about that second mode with one observation. But it's all hard. All right.
Yeah.
So there's a slide saying, we do have to clear out some unnecessary topics. I put nothing really controversial there, except maybe the last one. I put probability in there. Testing mean with sigma known, shortcut formulas, all that stuff, gone. So this is what we've been talking about, statistics as problem solving. Isn't that what you've been saying, Paul?
Absolutely.
This is what it is. So I just have to tell this first story. This is a real story that I had at the First USA Bank, where I was talking to the CEO, and he was asking about the sample size. And sample sizes are wonderful at credit card banks. They're not like pharmaceutical. They're in the hundreds of thousands.
Right.
I could say 100,000. I say, We can do that tomorrow. I love it. It's just junk mail. So I said, well, Rick, let me ask you. I said, you're really excited about this new offer. He said, oh, yeah, I think this is going to be great. I said, okay, well, we're going to send out 100,000 of these, 50,000 tests, 50,000 control. We're going to see how it works. I said, so if the data from this tell you that it works, what are you going to do? And he said, well, then we're going to roll out this idea to our 10 million customers next week. And I said, well, that sounds sensible. I said, but let me ask you this. What are you going to do if it says that it didn't work? And he looked at me really strangely and almost like he was hurt, and he said, damn it, I think this is a great idea. I think we're going to go ahead and roll it out anyway.
Right.
Right. I said, you know what? We can save some time here. So, always a good question to ask before you collect data. What are you going to do with it? What's the decision, and what are you thinking? So, this is all about models. I'm going to kind of try to wrap up here. You know, I remind them about. Everybody knows George's first quote, but I don't know if everybody knows his second. It's my favorite. Statisticians, like artists, have the bad habit of falling in love with their models. And we're dealing, you know, I think it hit me when I was at the engineering school at Princeton, when I was thinking about why this whole idea of parameters is hard for students and populations. And it's because populations don't have parameters. And I was looking in the soil for the diffusivity parameter, and I was digging, and I couldn't find it. And I realized populations don't have parameters. Models for populations have parameters.
Right.
And if we just say that, instead of saying that the populations have parameters, no, it's some model that we have.
And that's smart, yeah.
Yeah, you know, and then they go, oh, okay, that's just the math part. I said, right, we don't know if it's right, but it may be a good model. We have a new guy who's coming. He's a mathematician to our department, but he really loves to do baseball statistics, which is kind of a mixed blessing. I mean, it's good and bad. He doesn't really know statistics, but he's really bright. And he was saying, oh, these sabermetricians, these are the guys who do this stuff all the time, of which I was a card-carrying member for a while. He says what he doesn't like about him is, he says, they come up with rules just based on the data. And I looked at him and I said, as opposed to what? And he said, as opposed to modeling.
Where did the models come from?
Wasn't that great?
Yes.
I just said, oh, boy, we're going to have some great conversations. Right. Can you imagine that, using the data instead of the models? I once had a famous physical scientist yell at me when I was talking about looking at satellite data around Antarctica, who said, why are you looking at satellite data when we have perfectly good models to tell you what's going on down there?
Oh, dear. Where do they think their models came from?
Yeah, well, some of them didn't. I mean, you know, we could talk about economists, but we won't.
We won't go there.
Let's not ruin a beautiful afternoon here. So here are our models. I mean, I talk about them right up front. Regression models, histograms. Then we've got sampling distribution. For some reason, it's clicking away. There's something wrong. That's okay. We're running out of time. So let me just give you the bottom line. This is the answer to Catherine's question. I think if we talk about models early enough, that by the time they get to sampling distribution, we're not adding three concepts at once.
Mm.
That's the only thing. I mean, it's the lump in the rug. It's, you know, it's when I go from most people's best friend to everybody's worst nightmare, is that sample distribution chapter. But if they're used to models, if they're used to idea of variation, if they're used to samples being random, we get all of that done, then when we throw that sampling distribution model on them, at least it's only one hard, profound concept extra.
Mm-hmm. Mm-hmm.
And I also say that's the way to look at null hypotheses, of course. It's just a model. And often we hope it's wrong. But that's what we're going to test. We're going to go with that model, and then they don't feel so bad about letting it go because it's just a model.
What do you say when they say, well, why don't we make what we think is true the null?
I go back to the jury for that.
Mm-hmm.
Is that convincing? Let's assume, you know, I usually pick some.
Yeah, I think it is.
Row and then say, okay, we can assume he's guilty and how. And the other thing I give them is De Veaux's theory of the universe.
Which is?
Help us.
Which is that all the heavenly bodies revolve around me.
Okay.
And I said, this is my theory. And I said, you know, and all you people are lucky enough to be near De Veaux. So you, it will appear that the heavenly bodies are rotating around you as well. And I want you to go check. If that's true, then the sun will appear to rise in the east and set in the west every day. I want you to collect for the entire semester. And at the end of the semester, we'll test the model. Are you convinced? Will you be convinced that De Veaux's theory is right? And, you know, I mean, enough silly examples, and I think they start to wear down that maybe that's not the best way to do science.
Mm-hmm.
Assume that we're right. Of course, then we get the chi-square test. Right? Oh, it's not an easy task. All right, so I think we're all sold that we're not going to do calculation by hand.
Right.
And all right, so we can just and this I think gets back to what somebody said about what are we trying to teach. I like questions like this that emphasize the concept of standard deviation instead of the formula. So this is, you know, a friend says that there's a study about teaching experience about professors. He knows the mean, but he can't remember whether the standard deviation was 6 months of teaching experience, 6 years, or 16 years. Which one do you think it is and why?
That's a great question.
That is a wonderful question.
And there's a great book. Princeton University Press people just came to me, and there's a great new book that they've come out with called Guesstimation. It's full of stuff like this. I mean, our students are so bad at this these days. They don't want to guess anything. They want to go right to their calculator.
Is this book in print?
Yeah. I'll send you the link. I'll go look up the exact title. I have it at home.
If you can send it to everybody, that'd be great.
Yeah, I'll send it to Rick and.
No, send it to Rebecca.
Oh, Rebecca. Thank you. Okay. Great. Okay. So, some other things. Communication. Somebody pointed this out when my book first came out. He said, you know, it's great to say plot the data, but you have to tell them what to look for. Well, you're right. You know, that's a good idea. So let's tell them what to look for in all of these and why. It gets back to the why. What are we doing?
Mm-hmm.
And you know, rejecting the null hypothesis. You know, I like to tell you that I'm a student. One of my students got a first job and was supposed to test 10 different vendors on the efficiency of their product. And he did analysis of variance and came to the meeting and said, you know what? The null hypothesis was rejected. They're not all the same.
It didn't say anything more?
Yeah, that was what all the F tests that he learned said. You know, isn't that the end of the story? Maybe not. Maybe a confidence interval would be useful. Or an example that I had said we calculated something and the profit was going to be between minus $6 million and $12 million. So what do you do? But don't be satisfied with that. We have sections called What Can Go Wrong to try to point out all those wonderful mistakes. So we're here. Here's where I think we are. Is that, you know, we've said what's hard about this course because it's about the real world and it's not about the math. And for the math kids, I don't want to turn the math kids off. And I say, boy, math is really important here, but it's just not the message, no more than it is in physics or chemistry. It's really useful, but it's not what it's about.
Mm-hmm.
It's about understanding.
Mm-hmm.
And I think you guys have been great. I mean, you've said exactly this, the fourth bullet here. I'd love to think that at the end of the semester I've told the story of statistics so they get some idea that this is a way of thinking, not a bunch of tools. So it's not hand-wavy, as you said, not cookbooks that some of the kids think.
Mm-hmm.
And I think we already have Deming to tell us how to be better problem solvers, and that's our job here, that we're going to try to help them with all this strange thinking that we're trying to do. But if anybody has any ideas of how to do this in 12 weeks, please let me know.
We're all struggling with the same problem.
Yeah. So that's it.
Thank you.
Thank you.
Thank you so very much for your presentation today. It's been very insightful and very helpful. Ladies and gentlemen, thank you for joining us today. And Rick, if you'll push the button, we'll sign off now.
I'll do that, Paul. Thank you. Have a good afternoon.
Thanks.
Take
Rebecca,
care.
call me,
Bye-bye.
Rebecca.
Okay, bye.
Bye, Dick.
I will.
Bye,
Call me,
Rebecca.
Rebecca.
Bye,
Bye.
Paul.
Okay, I will. Thank you.
Call me,
Thank you.
Rebecca.
Good night, John
Okay,
Boy.
okay, thank you.